For centuries, what we knew about our environment was simply what we could see and sense around us. Today's weather was easy enough to see. Tomorrow's weather in the hands of greater powers. Ben Franklin was one of the first to observe that storms travel across the surface of the earth. That was in the 1700s. But not until the 1800s, the age of enterprise, would Mr. Franklin's observations be supported. The 19th century was a time of thinkers, tinkerers, a time when technology broke into all areas, and meteorologists drew their first weather maps. The maps gave the first clues as to the broad nature of weather systems. In the beginning, they were strictly research tools. This map was made using observations taken 3 p.m. August 11, 1843, but it wasn't drawn until 1848. A map of the weather 5 years ago will not help with tomorrow's forecast. In order for these maps to be useful to a forecaster, someone had to find a way to collect current observations on a timely basis from a wide geographic area. That would take a modern communication network. So weather forecasting was born on the lines of the telegraph. In 1870, the Western Union Telegraph Company produced daily weather maps, charting temperature, wind direction, and cloud cover. That same year, because of a rising number of shipwrecks on the Great Lakes, President Ulysses S. Grant signed a resolution. It required the military to take meteorological observations and give warning to the approach of storms. In effect, a national weather service was started. It's been almost 120 years since President Grant's mandate for the taking of meteorological observations. I think he'd be quite pleased with the system we have in place today. We're here at the National Weather Service office in Athens, Georgia, housed in its local airport. It's one of 230 such offices around the country taking observations systematically throughout each and every day. Meteorologists like Greg Hansen record the hourly temperatures, the humidity. They check altimeters for the air pressure, eventually a visual state of the sky, the height of the cloud ceiling, any precipitation that has fallen. All of this information ends up in the hourly surface observations. The Weather Service codes and enters the information into a computer system which links Weather Service offices together. The computer transmits the message to the National Meteorological Center in Suitland, Maryland. Here, meteorologists plot those observations taken at the same time from all over the country. Now the process of making some sense out of all this data begins. One of the first steps in analyzing a map of observational data is to draw isobars on it. Iso meaning equal, bar for barometric, lines of equal barometric pressure. It's a lot like playing connecting the dots. The lines connect observations of equal barometric pressure. The pattern that emerges shows a kind of topographic map of the atmosphere. It shows peaks of high pressure and valleys of low pressure. On this map, the isobars encircle 3 areas of high pressure. But what is a high pressure system, and how does it form? Air masses get their physical properties from the land or water they are borne over. If air sits over very cold terrain, it cools, compresses, sinks. It will pile up until acted upon by forces of nature. It starts to move. The air within a high-pressure system is not stagnant. Imagine we are riding a gust of wind down this mass of air. If the Earth did not rotate, then we would merely slide down the dome, like water running down a hill. But our planet does rotate. So in the northern hemisphere where we live, our gust of wind is deflected to the right of the downward path. This is a law of nature known as the Coriolis effect. It causes the winds in a high-pressure system to rotate in a clockwise direction. Now, let's put our high-pressure system back on the map where we found it. The weather within the system is cold and clear, like this beautiful day in Denver. The 3 systems on our map have very different characteristics. The high in the southeast has picked up warm, moist air from the Gulf. The air mass to the north is cooler, but it has been weakened by a long trip across the continent. The boundaries where these 3 air masses collide are called fronts. If 2 air masses are of equal strength, then the boundary will be a stationary front. symbolized by a line with blue spikes and red rounded symbols. But on this particular day, the cold high was dominant, its pressure greater, so it developed a cold front. The blue spikes of the cold front indicate the direction it is moving. Cold air is moving in, pushing the warm air up. Meanwhile, the warm air mass is overtaking the cooler air to the north, resulting in a warm front. That's shown as a line with red rounded symbols facing the direction the front is moving. The warm air is riding up over the cooler air at the surface. At this point, the air circulation around the highs is developing a frontal wave, creating a low pressure center. The wind circulation in a developing low is the